So today's lecture is another exciting lecture on long context models. And so this is another really active area of research. If you use things like language models or agents, you might frequently run into the issue of them kind of running out of context. So you might have already run into this problem before in practice. And there's really a lot of interesting ideas and modeling choices you can make to try to support really long sequences or long contexts. So hopefully you'll have a really good understanding of that after today's lecture. So the first question is, well, when we say long context, we mean kind of long sequences. And the question is like, how long are different sequences? So if we consider maybe the traditional setup for NLP, back in the day, we were doing things like translating a single sentence, and that might just be, say, 20 tokens. And of course, now if you use something like ChatGPT or some agent, you're operating on much kind of longer sequences. So for instance, a document might be 100, a short document might be 100 tokens, longer one might be 10,000. And of course, you can make even longer documents than this. If you consider a book, now we're at another order of magnitude. You might have 50,000 tokens or 300,000 tokens. And of course, these are maybe relatively short or kind of medium-sized books. So you could definitely find books that are much longer than this. In this course, we've also gone over, I mean, most of the techniques that we've gone over in this course are not really specific even to sequences of text tokens, right? As long as we can kind of represent some modality in tokens, then we can at least think about applying the methods we've talked about. So let's think about kind of tokenizing a video and modeling a video. Well, then, as you might imagine, this can get really long. So up to 1 million tokens for even a relatively kind of short video. And if you had like a full movie, then it would be just really large number of tokens. Another really common use case is having an agent or a language model operating on a code base. So now instead of just kind of getting some prompt and generating a function, now we're in these much more realistic scenarios where you might have, your company's custom code base and the model hasn't trained on it, so you want the model to kind of take in the whole thing and then give you useful suggestions. I think I got this number from someone from a blog post. I don't think I imagined it, but something like these really large code bases, like all of Google, might even get up to, say, 1 billion tokens. So very large. Then also at the end, we'll briefly see results where they take the model and basically train it on another type of language, if you want, which is these kind of genomic sequences. And these can also be very long. So here we might have in one genome 3 billion nucleotides. And so if you want to generate or even just like classify different things based on an entire sequence, you have to be able to support very long sequences. Then the question is, do we actually have to do anything different? Well, the answer will be yes. So why is modeling long sequences actually hard? So first of all, mainly we've been dealing with these transformer models. And as we'll see later in detail, we'll go through this in detail, they scale quadratically in memory. So basically when we do this attention operation, we have this quadratic growth in the memory requirements. And it turns out that this actually is one of the main reasons why supporting long contexts efficiently is difficult. And so we'll walk through that in a bit. In addition to memory, there's actually performing the computation. Here, the transformers are also scaling quadratically in the amount of computation. So we will also take that into consideration. And then another thing is, I mentioned like a code base with 1 billion tokens. Maybe there's actually not that many of those. And so just getting training data that is kind of truly long context might actually be kind of difficult, especially for a very specific use case. And so it turns out that training data is kind of lacking, or the signals that you get by just applying a standard algorithm might be weak. And then if we want to actually train on these long sequences, then it's very costly. So this is going to be another challenge that we kind of have to deal with. So we'll go through a variety of strategies to tackle these, but first I wanted to just give some intro to different ways, different tasks, and different benchmarks, things like that, for this kind of long context setting. So I'm writing here early benchmarks. These were maybe from like 2 or 3 years ago. So some early benchmarks are, okay, 5 years ago. This one called Long Range Arena. And here they came up with these tasks that kind of by definition would require kind of referencing information from a long sequence. And a lot of these were non-NLP tasks. It might be kind of synthetic tasks, things like that. Here's one which is maybe looking at some more NLP style tasks. So here we have a really long context and we want to say summarize it, or we want to answer questions about it. So on data sets called scrolls. So here on the x-axis, we have the number of words in the input. So this would be the kind of context size. And here you could see that for this QA task in scrolls, it is between 10 to the 4 and 10 to the 5. So at the time, basically the best model that was available didn't support context lengths of that size. In addition, there was this kind of really interesting finding in 2023, and they took again the best models that were available. Now it's GPT 3.5 Turbo. And just even with like a very artificial task, you can kind of demonstrate this. And they basically found that, okay, if you feed in a really long context to a model, then the kind of creator of the model might claim that it supports the long context, but they found that often the models were kind of biased either to the very beginning of the sequence or the very end of the sequence. So they call this phenomenon kind of lost in the middle. Okay, so the model was failing when the answer was occurring, say, in the middle of the context. Now you can imagine that once someone points this out and the paper becomes very famous, probably this has been addressed or fixed in different models. But this was kind of, really interesting at the time. And of course, as we'll see, I'll show some really recent results. Models are still not perfect on even relatively kind of simple tasks. So here's a really simple task which has been used to probe the use of long context in language models. And it's called needle in a haystack. And so here what you have is, let's see, on the x-axis, you have the context length again. And then the task is to basically, you have this really long document. And then somewhere in the document, you just place a kind of keyword or something like that. I always forget exactly what it is. I think it at least used to be about Paul Graham, this venture capitalist. And you basically have to say, the magic word is XYZ, and you just place it in a document, and then you prompt the model to say, what is the magic word? Something like that. And so when this first came out, again, you could find these kind of failure modes in the different models. Here it was succeeding at the task, further back in the context at maybe, disjoint positions, it was failing, things like that. This is also really simple and popular to run. So after this came out, the kind of new versions of the models, you would read their paper and they would have this green block where they kind of solved this probing task. So since then, you could think about making this a bit more difficult, maybe. Maybe you could have multiple needles or you can kind of aggregate information over multiple points. And so here's just another reference. You can take a look at this paper called Ruler, basically compiled a number of these different needle in a haystack tasks. So I'll give one more really recent example, but before that, there's one thing in between. So another thing you can do is also try to kind of show the use of long context by testing this kind of many shot learning setting. So we actually saw this in the prompting lecture. This is a different reference. This one is from here at CMU, Amanda Birch. So here they found that as you increase the number of examples in the context, you can see that the model's accuracy is improving. And in particular, sometimes they're even able to beat fine-tuning using just the in-context learning. I guess this would be showing that the model actually is capable of leveraging information from the examples in the context. Here's some other tasks. So another is dialogue. So as you probably have encountered something like ChatGPT, you have a dialogue with it, and over time it gets longer and longer. And so then the question is, can the model kind of use long-term context from the conversation? So here is a data set released in 2024, and they have these different conversations. And then you could basically evaluate different tasks. So you could, ask questions about the conversation and construct the questions so that the model has to reference information in it. You could have a summarization task or just a response generation task. And then they'll kind of pick the examples such that the model would have to kind of reference information in the long context. Okay, so here again, you can take a look at these, and there's probably been follow-ups since this was released. I wanted to put one example that was very recent. So this paper was actually, I think, from last week. And this is again from Amanda here at CMU. And so they constructed this data set or benchmark, and it's called Oolong. And the idea is there's been these needle in the haystack tasks, but they observed that none of the existing ones really test specifically the ability to aggregate information across multiple places in a long context. So what they do is construct two different types of data. So first they have a synthetic task, which is you could take, let's say you have a document and you have a classification task for the document. Like, I don't know, what is the sentiment of this movie review, something like that. Well, then what you can do is you can just concatenate like 100 of these different tasks together. And then you can ask a question like, what is the label for all of the documents in the context? In order to solve that, the model has to basically internally classify each document, and then it has to aggregate the classes and say, oh, it's 50% positive, 30% neutral, 20% negative, something like that. So you can construct different tasks like this where the model is basically forced to use information from across the context and kind of aggregate it together. Then here what they did is they also took some real data. So apparently there's these Dungeons and Dragons transcripts, and they're really long. Like here it says 12 hours. And so you basically have these dialogues of people talking, and then you can ask like specific questions about things that occur in the dialogue. So here it's asking like how many times does this character cast this specific spell? And so, right, the model has to basically look over the entire dialogue and then answer this correctly, and it's really easy to evaluate. So kind of clever and kind of really nice intuitive thing that it's evaluating. So then again, this is really recent, so it's on the kind of newest models, and you can see that the performance on both the synthetic data and the real data, I mean, it's non-zero, but it's actually decreasing as the context length is growing. And no model is kind of doing perfectly on this. And so, yeah, even for the kind of tasks they constructed, it's clearly the, models are not yet perfect at kind of leveraging the context. So that was a kind of quick overview of some different areas. So one that I didn't make a slide about, but one that is definitely taken in or kind of falls into long context or long sequence modeling is the agents. So let's say you have a coding agent. I don't know if anyone's used something like Claude Code. Then if you use it for a while, you're interacting with it. It's maybe looking at your code base, generating edits, things like that. And eventually you get to the point where it runs out of context, and then it just you can either just delete everything or compact it down somehow. Similarly, let's say you have a web agent or you have this computer use agent. There again, I mean, in the case of computer use, the model is seeing some screenshot at every time step. And so you have to do something to kind of reduce the context length. You might just save the chain of thought that the models produce, something like that. But in some sense, those are discarding some of the available context that you could feasibly use. So again, in these agentic tasks that are really the active area of research, this issue of having really long history or long context is very much there. So before I go to the next section where we'll start to talk about techniques for addressing long sequence modeling or long context modeling, anyone have any questions? Mhm.
The needle in the haystack diagram, models were doing better if the needle was um, towards the start of the document. Like this is skewed towards the start of the document. Much like they're doing worse when the needle is in the start of the document,
Mm.
right? So any reasons as to why that maybe?
I see. So yeah, here is context length, and then here's position in the document.
Yeah.
In case, yeah, it's kind of small. So here's the top, and then here's the bottom. It might relate to this up here. So this was the kind of finding at the time that models would basically struggle if the relevant information was in the middle. And then you can see that at the beginning, it's also higher than at the end. So I'm not sure exactly the reason. It could be that a lot of the model's training data is actually not really long context. Like a lot of the times you can predict the next token by just looking in the set of, previous tokens. And so possibly after training just on so much data, the model has become biased, its attention patterns are biased to looking, in a
Closer.
closer context. Yeah. So that would be my hypothesis, just thinking about it right now. Okay, so next we're going to go over two classes of approaches. So the first, well, two classes, and then in the first class, there's three different kind of strategies. So the first is really aimed at taking transformers and trying to improve them. And then at the end, we'll talk about using a different architecture, so not using transformers in the name of having something that hopefully works better on long contexts. So we'll talk about memory efficient computation and extrapolation. And I'll probably skip over these, but they'll be in the slides if you want to look over them later, so that I can be sure to have time to talk about the methods at the end. So here we'll talk about these state space models. So it takes a bit of time to kind of go through it. Okay, so first the memory efficient computation. So really the issue here with the transformers is we can take a look at this attention operation. And hopefully this should be familiar by now, right? We had this in the lectures and in the homework. And so here's really the key operation where we are getting these scores, right, by taking the dot product between the keys and values. We're taking the softmax, and then you could take the weighted sum of the values using these attention scores or kind of outputs of the softmax. So we could take a look at this operation, and here you have this matrix multiplication. And so here it's a kind of tensor, you have a batch size, you have the sequence length and you have the hidden dimension. Here we're taking the transpose. And so you, at the end, get something which is like sequence length by sequence length, which makes sense because each position in the sequence, you want attention scores for the rest of the items. And the compute that's involved in doing that is written right here. Then you can consider the memory. And here you run into this quadratic use of memory as well. So here you have some intermediate computations, and then you have the final computation. And so again, we end up with something which is batch size times sequence length squared. And we'll have to store that in memory. And so this will turn out to actually be a kind of issue, which we'll talk about in a bit. Now, if you have this actual just matrix multiplication here, so this is A, then this again has the same computational complexity, and the memory will be kind of lower because now we're reducing this kind of sequence dimension because you're doing the weighted sum. So really we want to focus on this and potentially come up with ways of reducing this computational complexity or memory requirement. So before we talk about that, it turns out that things actually get worse if you have multiple attention heads. So here, if you remember, when you're implementing it, you can kind of just reshape and do a similar matrix multiplication. If you think about how much memory is being used, then essentially by increasing the heads, you are adding on this extra term for the memory. If you want, though, you could kind of consider what happens if you just reshape the matrix and view the memory that way. So what is the issue here with memory? So this is a really nice plot and it's from, or a figure, and it's from this paper, and you may or may not have heard of it. It's called Flash Attention. It's a really influential paper, and we'll actually talk about it later. So here they have the kind of memory model for a CUDA GPU. And you could see that it has three different parts. So up here you have this memory SRAM, and it's really fast. So here you have what's called the memory bandwidth. So how fast you can kind of transfer data. And it's 19 terabytes per second. It seems pretty fast. The trade-off is that it's very small, so you only have about 20 megabytes of this really fast SRAM. Then the second level down, you have this HBM, and you can see that the memory bandwidth is lower, but it's much bigger. You might have, say, 40 gigabytes with this particular GPU. Then down here, you have the CPU RAM, and you could see that you really don't want to have to write to CPU memory. Now, instead of terabytes per second, we're dealing with gigabytes per second, 12 gigabytes per second. And of course, the benefit is that you could have, say, a terabyte on a really nice server of this CPU memory. Okay, so the challenge will be how do we kind of do all of our operations in the fastest possible memory? Because otherwise we'll have to incur these transfer costs, kind of communication costs, due to the limited memory bandwidth. So if you think back to 2 lectures ago when we talked about scaling up the language models, we were talking about these communication costs that involved multiple GPUs or multiple devices. But it turns out that we actually have to consider the communication costs even within a single GPU based on what kind of memory is being used and transferring between them. So basically what happens is if you have this memory requirement, which is quadratic in the sequence length, then if you just make the sequences longer and longer, eventually you'll get to the point where you can't perform this operation in the really fast memory. And so you have to transfer to this HBM, and that will really slow things down. Okay, so the first time I saw this, or if this is the first time you've seen this, it might be kind of counterintuitive that it's not necessarily the computation that's involved because the GPUs are kind of built to do these parallel computations. Of course, that can slow things down, but really a big bottleneck in practice is going to be these kind of memory transfers. And again, the amount of memory that we need is going to grow based on the sequence length. So as a result, it becomes really expensive to pre-train a transformer with a long context length. Again, if you remember 2 lectures ago, we basically viewed pre-training as trying to process as many tokens as you can, just in the most efficient way. And so if you have this really, if it slows things down to just increase the context length, then that's not going to be a very good trade-off to make. Also, if you're generating, this is going to slow things down. Let's say you're generating and you have really long context, or you're generating some really long chain of thought. And here, expensive can mean either two different things. It can mean that it is slow, so you're doing these transfers and the limited bandwidth results in slowdowns. Or let's say that your library doesn't offload to the CPU and it just crashes instead. Well, then if you use a large enough sequence length, then you might literally just not be able to run the model. Okay, so hopefully you have some idea of the kind of specific technical challenges that come up with transformers and the long contexts. So now we can look at this kind of clever way of overcoming this. And again, if you look at the formula for the attention, it's just this one matrix multiplication and a softmax. So it's actually not clear kind of what we could even possibly do. But it turns out that there's this kind of really clever solution. So the insight here is that it's actually possible to compute the softmax online. And so if you're able to do this, then it turns out that you never have to store this S squared size matrix in memory. And so this goes by the name of, well, it's called various things, lazy softmax or online softmax. And there's might be an earlier paper that did this, but there's this reference from 2019. And then here in 2021, these two researchers from Google basically used this in the context of implementing efficient attention in a transformer. Actually, the paper was just on archive. It was never published or anything, but it's still, yeah, really interesting. And as we'll see, it kind of is used now in a lot of different places. So again, here the trick is going to be, okay, you can consider this after you take the softmax, then you can break it down into some numerator and some denominator. And it turns out to be able to compute this with only this kind of linear amount of memory, linear in the sequence length. So here we have the numerator of a softmax, and here you have the denominator. And so the goal will be to compute each one of these and then just divide at the end using only the linear amount of memory. So here's the kind of algorithm, and it kind of goes one query at a time, right? So we have a query for every item of the sequence. So the trick is going to be you can go for each given query, you can take the dot product with, so this is for a given query, sorry. We're going to go over in this loop and take the dot product with each key and get this weight. Then you can basically accumulate this result into this buffer. So here we have the weight and you have the value and you're taking the exponent. So you can see that it somewhat looks like what appears in the softmax, and you're basically accumulating it into this buffer. Similarly, for the denominator, you are also accumulating this buffer. And then it turns out that this algorithm, if you divide the numerator and the denominator, it turns out to be equivalent to the attention operation. So multiplying the keys and the queries and taking the softmax. So to really kind of internalize this, you probably have to go and look through the paper and think about it for a bit. It's a bit unintuitive, but basically you are able to compute this operation in this online fashion. And you could imagine that it probably slows things down because now we have this kind of loop. But the key thing is it slows things down, computationally. But the key thing is that now we're just storing this kind of one piece of memory, which is linear in the sequence length. And so you avoid this kind of quadratic growth. So this is really the key idea. And then you can imagine like, okay, once you point this out, then you could try to get more clever. So then it turns out that instead of just separating things into like an individual query and individual key, you could think about segmenting things into blocks or tiles. And then like what is the optimal block size or tile size? It's not necessarily just one item. It could be a group of items, something like that. So that's what they actually do here. They have this kind of online softmax and it's broken up into different tiles. So now we could look at the results, and here we have the standard attention and we have the memory efficient version. And up here we have the sequence length, and this is during inference. So you can see here that if you get up to 1 million tokens, then you simply get out of memory. This was actually on a TPU versus a GPU, but you ran into similar issues. And then you could see with the efficient attention, now they're able to fit this 1 million, or they're able to do inference with up to 1 million tokens, and it just requires kind of 256 megabytes. So really cool. And this was, back in 2021, they're already experimenting with kind of 1 million token size context length. So they also demonstrated that you could do this for training, so not just inference, and empirically you can get these, or you could have this ability to basically train on longer sequences. So then, since then, this idea has shown up in other areas. So if you look in the flash attention paper, for instance, then flash attention, it's amazing. They do a lot of different things. One of them is to basically incorporate this online softmax trick. And they write this CUDA kernel so that you can manage the memory of the GPU device kind of optimally. And again, they kind of break things up into tiles and do this online computation. And that's really needed to implement this flash attention. Flash attention then enables you to speed up inference, speed up training, things like that. And so soon after flash attention came out, it was incorporated into all these different libraries. And I think now it's at flash attention 2 or 3 or something like that. Also, I'll talk about this on the next slide. You could imagine that, okay, now that we can break up this attention into a kind of streaming fashion, then what we can do is actually put each one of these blocks or tiles onto individual GPUs. So now we could basically break up the computation of attention on multiple devices. And so this might be needed if you have kind of really large sequences with really large models. You have to actually distribute the computation across multiple devices. So that goes by the name of ring attention. And so here we can go into it in a bit more detail. So one reason that this is interesting is it kind of fits in with the lecture from 2 lectures ago. So you could view this as a kind of new dimension of parallelism. The idea is you have this really long sequence and you are splitting up the computation of the attention on the multiple devices. So that's a bit different than what we saw like pipeline parallelism or data parallelism, things like that. So you can kind of call this context parallelism. So the basic idea is each one of your devices or hosts will host one query block. And then if you go back and look at the algorithm from before, remember for a given query, we're basically cycling through the different items and doing the dot product with the different keys, and then the value was showing up as well. So this kind of hand waving that I'm doing is kind of what is being implemented here. The idea is the keys and values kind of pass around in this ring, and then eventually each device has kind of multiplied its block by the keys and values, and then at the end you can kind of aggregate the results. So it's really clever. It's called ring attention, and again, you could view it as being another dimension of parallelism or another strategy that you can mix with the other stuff that we were talking about 2 lectures ago. So here's some results. And so here we could see, for instance, okay, no parallelism, not a good idea. Here we're trying to use the tensor parallelism. And you could see that as the sequence length is going up, it's still out of memory. This is during training, so you have the activations. And now we are increasing the context parallelism to 4. And these have been reduced. There's still expensive, but at least now we're able to train, say, with 16,000, whereas with just the tensor parallelism, that wasn't feasible in this experiment. So that's the idea of ring attention or context parallelism. And this is again from the same book, so you could view it as another kind of strategy. So I think if you look at the paper that proposed the ring attention, they also test the model on sequences with millions of tokens, and it might have been videos, something like that. Okay, so any questions so far before I go to the next section?
How does flash attention compare to ring attention? I mean, are they like comparable or can you maybe do both at once?
Yeah. Yeah, so flash attention is going to be for a single GPU. Kind of how do you manage the memory of that GPU really well? So it's implementing this softmax, and then it is ensuring that everything is in the really fast memory. So it should be complementary. You'd have to look at now that I'm thinking about it, yeah, you'd want to make sure that the computations that are involved in ring attention would allow you to still run the flash attention kernel. So maybe out of the box, it's not compatible. But in principle, the idea of like optimizing what you're doing on one GPU versus how you're splitting things up across multiple GPUs, you should be able to do something complementary. Yeah, that's a good question though. Okay, cool. So next I'll talk about extrapolation. So extrapolation refers to, let's say a model is trained on, say, 4,000 sequences of length 4,000. Now someone gives you an input and the length is 4,001 tokens. The question is what happens? Does your model blow up? Does it fail? Kind of what happens? So if the model is able to extrapolate, then it will basically be able to function well on sequence lengths that are longer than what it was trained on. So again, let's say we train it on documents of length 4K. Now at test time, we give it a document of length 5K, and it's able to still kind of function properly, use information from this longer document. So what happens is the positional encodings end up being kind of problematic, or you have to think carefully about what you're doing for the positional encodings. So if you remember back to the transformer lecture, we introduced this idea of using these really simple absolute positional encodings. So this basically says for positions in this example, 1 through 4,000, we're going to learn a vector that corresponds to the given position. So you have 4,000 vectors. Now, if you get a document that's of length 4001, well, now the model basically gets, say, a random embedding for these new positions. And now it's kind of out of distribution, and typically the model will just fail. So this learned absolute encoding or positional embedding is not really a good solution. So the fixed absolute encodings, so we didn't go into detail this semester, but in the original Transformer paper, for instance, they have these positional encodings that are based on kind of like sine functions, cosine functions, and they have this periodic structure. And the hypothesis was that, since they're based on functions with a periodic structure, then they'll kind of extrapolate because the functions are kind of, have these symmetries. What happens is that when you combine these together into some embedding, then still the point that the model gets when you get to a longer context length is still new. The model's never seen it during training. And so it kind of moves out of distribution and you still see the model failing on longer context. So unfortunately, those types of embeddings, if you're familiar with them, don't turn out to be the answer as well. Similarly, the relative encodings, so say some kind of early one, like pre-rope encoding, which was looking at nearby positions in the like attention operation. Or it turns out, as we'll see, even the rope embeddings, in theory, it seems like they should be able to extrapolate because you're kind of shifting this relative uh, encoding around. But what happens is that they still fail. And so one possibility is that the model can actually get clever and kind of figure out what absolute position it's in based on a variety of information. So for instance, the model can look and maybe like certain types of information is usually at the beginning or at the end, and it can kind of work out where it is in the sequence. That's one possibility. Another that we'll see is that there's this kind of flaw in rope that the magnitude will naturally go down over time. So here's a concrete example, and it could be kind of really striking. So here they have a model which is trained with rope, and it's been trained on 32K sequences, and then they tested on longer ones. And you can see that the rope embedding actually does extrapolate a bit. So potentially, since it's relative and it's also based on these kind of periodic functions, it is able to actually get some extrapolation, but then clearly it's just not doing very well as the sequence like exceeds some limit, about 40K. So there's kind of two different approaches you can take to this, or at least two. So the first is maybe kind of obvious in retrospect. You can just train on longer documents. So if the model has been exposed or trained on longer documents, then the embeddings are kind of adjusted to those, and your model should kind of work on the longer documents. So here you have to think about where you get the data. And so sometimes it could be tricky again to find like real data that's a lot of real data that is truly kind of long context, has these long context dependencies. So people will do different tricks, like they'll upsample longer documents, or you could just synthetically make a document longer. And yeah, anything that involves data usually involves, a lot of trial and error on what you should do. But then you could see that as long as you can kind of computationally do the fine tuning or post training with the longer context, then here, even with the standard embeddings, it's kind of fixing the issue in the sense that now you can support 128K. The issue that it's not fixing is this isn't necessarily going to extrapolate to, say, 256K. You have to keep, post training on longer and longer documents. So the other thing you could do is take a look at the position embeddings. So again, if you remember, these rope embeddings have this form here. You have these sines and cosines, and then this parameter theta impacts the periodic structure or the period of the function. And so here you can parameterize theta using this form here where you have this base. And say in practice, you might use a base of 10,000. And then you have these two other items which are based on the positions. So one way to visualize this is you could have this kind of cylinder, and this theta parameter kind of controls how fast the rotation is occurring. So people took a look at these rope embeddings and kind of multiple groups identified issues and different solutions. So one thing that they noticed is that based on how rope is formulated or what was learned, it is kind of naturally decaying as the sequence length is increasing. And so possibly this could affect things because just the attention scores are here the attention scores are just getting very low based on the distance of the query and key tokens. And so this is kind of concretely showing one issue that you could try to fix. We basically don't want the attention scores to vanish as the length is increasing. So there's kind of at least two different things you can do. One is you can increase this base frequency. So in some sense, it's maybe staying in a similar range, but now you're kind of sampling the points more frequently. And this turns out to be somewhat effective for kind of overcoming the issue. So specifically, this would be in a kind of post-training setting where the model's been trained with one base frequency. And now as you're post-training it on longer outputs, you would increase the frequency. Similarly, you can also adjust the period by some constant, and this technique is called position interpolation. So again, I'm not going into too much detail here, but if you want, you can take a look at these papers, and you can, to some extent, alleviate some of the issues with rope by using one of these modifications. Okay, and then the third class of methods, I'll just put them up really quickly, but we won't go into details here. So basically there's other things you could imagine doing. So you could imagine making the attention operation sparse, or having this sliding window attention, or even doing compression or approximations, things like that. And so if you read a paper, say like a paper about the latest Mistral model, for example, you might see some of these techniques come up. It'll kind of vary based on, what they chose to do. Another thing to be aware of is to look at whether the modification is approximate or exact. So for instance, if you introduce some approximation to attention, then maybe in the long run, you're kind of losing out on some modeling capacity. So in the long run, the exact methods might tend to win out. However, it's often kind of a trade-off, and you kind of figure out what works best for the model that you're training. So again, I'm not going to go too much into detail here. These slides were from Graham from a previous version of the course. So the reason is I wanted to make sure we have time to go through the transformer alternatives, specifically the state space models. So here we're trying to do something maybe ambitious, which is switch the architecture from transformers to something different. And the state space models were really kind of pioneered by Albert Gu, who's now here at CMU. So if you remember, we had this lecture on RNNs, and maybe at some point I said this will be relevant later in the course. And so actually what we're going to see is kind of uses a lot of similar ideas or kind of similar principles come up with the state space models as with RNNs. So if you remember with RNNs, we had this hidden state that was kind of being transformed over time. And then you have some output layer for actually making some prediction. And if you remember, the kind of nice thing about these is that, at least in theory, you can get kind of infinite context with the RNN. In the sense that, in theory, the RNN could learn to, at each time step, kind of retain the required information and add new information and kind of just keep passing this hidden state. And you can kind of just keep doing this forever. Similarly, in order to perform inference, regardless of how many previous tokens there have been, all you need with the basic RNN is this one vector. And so you have this nice constant memory requirement. Of course, in practice, it's kind of not as straightforward as that. So first of all, it can be difficult to parallelize the training of these RNNs. Well, that's maybe not related to this infinite context thing, but it is hard to parallelize the training, as we mentioned, unlike the transformer models. Also, with this infinite context, it turns out to be tricky. One thing is that in practice, the RNNs ended up using some attention mechanism because it was hard to kind of compress all of the necessary information, maybe into this one vector. Similarly, it was tricky to train the model. So there were different variants like the LSTM and GRU, but it tends to, get actually tricky in practice. So the state space models will try to get the best of both worlds. We'll try to have this kind of RNN-like inference where everything is just based on a single hidden state. But we'll also try to simultaneously have training that is parallelizable. So to do this, it'll also draw on ideas from convolution. So again, we never really went through this in too much detail, but if you remember, the basic idea is you have this kind of kernel, and the kernel is coming up with some representation based on some kind of window or local context. And again, you can kind of look at this and see that, okay, you can kind of parallelize this. You can break this into two different parts, and it's a bit different structure than the RNN. So, oh, and then this is just showing for autoregressive models, you of course have to like mask out the future. So the state space models will try to have kind of the best of both worlds, as I mentioned. So what is a state space model? Well, it's any model that takes a form like the following. So here you have this hidden state, and it's multiplied by some matrix. And you also have some input from the current time step. So you again multiply that by some matrix, and that will make up the current hidden state. So that actually looks kind of like an RNN, a kind of really simple linear RNN in some sense. Then here they also have this kind of skip connection. So your final output will be a kind of a function of the hidden state as well as this kind of skip connection. So let me show this in a couple different forms. So one thing you could do is say like, okay, skip connection is maybe an idea that's not specific to these types of models. So we could just consider this part as being the state space model, or this is kind of what we want to figure out how to do efficiently. Um, so yeah, from here on out, we'll just be considering these kind of operations in here, where you have this matrix A, which is modifying the hidden state, and then some matrix B, which is modifying the inputs, and then a matrix C, which is helping determine the outputs. So if you notice, this is using this notation where it's like a function of time. So really the kind of original state space models are these kind of continuous time models. So you have some continuous signal and your output is also a continuous signal. And you have these equations and they're kind of differential equations that are kind of governing the mapping between input and output. So the first thing you have to do is, we deal with these discrete tokens. So you have to somehow discretize. And the idea is kind of simple. So here you have some continuous signal and you basically sample at discrete time points. Or you consider, each time step to be some sample from the continuous signal. Now, if you view things in this way, then the question is kind of what time points do you sample from? And so we can call this difference between one time point and the next delta. So for our purposes now, we can just look at the state space model this way. And now you can see that it's starting to look kind of like some linear RNN. So we have a hidden state, you have some matrix, you have the input, another matrix, and then you have an output. So then what happens is if you kind of want to convert this continuous version to the discrete version, then here you have something which is kind of the rate of change. So you have to consider, yeah, converting this to something discrete. And when you kind of work out the math, this matrix here would correspond to this form here. So you have the original kind of continuous version, you have the granularity or the delta, and then you have this exponent. So I'm not going to go through like the derivation, but you'll see these equations come up when you're reading about the state space model. Okay, so now we basically have some representation of these two matrices in terms of these matrices and then this parameter delta. So again, we can kind of view this as being very similar to an RNN. So this is just showing you yet another representation of this equation. And yeah, one thing to note is that there's no non-linearities here. So everything is kind of linear. And the thing is that when you view things this way, it's again not really clear how to parallelize the training. So again, with an RNN, you can do efficient inference because predicting the output just depends on this kind of hidden state in the current position, but it's not really clear how to parallelize. So then the cool thing is the kind of insight with the state space model is that you can view this exact same model from a different perspective, from a kind of convolution perspective that you can take during training that allows you to parallelize. So here, what you can do is you can kind of view what's happening as being some kind of kernel. And so at one time step, you have um, this here, so like CB. And then you could see that as you move back in time, you're basically applying this matrix according to how far back in time it is. So this kind of follows from the fact that everything in the model is linear. And yeah, again, I'm not going to kind of walk through the full justification, but the kind of cool thing about this model is that they're able to view the same model equivalently as being this kind of convolutional operation. So you can see here that a given output is determined by these things here. I think there should be a square in one of them. And then these can kind of be broken up and just computed in parallel. So again, here, you could imagine this kernel being kind of really long, and you can compute these kind of however you want. And then you can do this, you can kind of view the entire model as being kind of applying this kernel to eventually get some output. Okay, so kind of zooming out again, the kind of interesting thing about these is that you could have this recurrent view, or you could have this convolution view, and both of them have kind of complementary trade-offs. So what happened is, like in practice, some modifications had to be made to get this to work really well. So there's been a few kind of improvements or variants on the kind of pure state space or discrete state space model. So the first thing that was done is called S4. And I think, so the S stands for structured state space. There's a fourth S, but I forgot what it is. But basically here they found that you can structure this. So this matrix A, you can see it's being kind of applied multiple times. And so it's important for kind of the memory retention in the model. And so what they found is that you can structure it in a particular way. And the P, one of the P's here stands for polynomial. So they basically show that you could use this kind of polynomial formulation or representation, and it was kind of better at retaining long-term memory. So again, not going to go through the details, but this was the paper that it's in if you're curious about reading about it more. And then a kind of really famous paper from, I guess, a few years ago at this point, or a couple of years ago, is a paper called Mamba. And so here, this basically took this S4 model, so the kind of improved state space model, and they added some ability to selectively retain the information. So we'll go through Mamba in a bit, but first I wanted to just introduce, well, we'll kind of go through Mamba precisely. So let me just introduce this kind of algorithm diagram. So here is with S4, and you can also see exactly what's involved in the state space model. So you could see here we have these different matrices that I was showing you in the slides, A, B, and C. And then what's kind of interesting is they treat this delta as a kind of learned parameter. So even though you're feeding in a kind of discrete sequence of tokens, the model can still decide kind of in continuous time how much of a transition would this be. Okay, now here you have these equations that I showed you before, and that will let you kind of discretize. And then you could pass this into the state space model. Okay, and then the key difference with the hippo is they're kind of structuring it, structuring this matrix A in some clever way. So then Mamba basically, oh, so one thing to note here is that these parameters are basically time invariant, right? So over time, everything is kind of staying the same, and the parameters aren't changing based on the current input. And so what you could view this as is being a kind of extreme, and it's kind of something we encountered with RNNs. You could view like one extreme as trying to have something that's time invariant and just like compressing everything into a hidden vector, and that's the only thing that's evolving over time. Or another extreme is like a transformer, where it's trying to attend over everything. And so every position is like looking at every other time step. And so conceptually, Mamba is trying to do something maybe a bit in the middle, and it'll basically introduce some time dependence into the S4 model. So what they do in the paper is they actually demonstrate that this S4 model would fail on these kind of synthetic or toy probing tasks. So for example, it would fail at this kind of simple copying from, I think, like really far back in the context. It would also fail on this task of induction heads, which is kind of related to just like repeating something in the input. And as a result, the model is like not that good at few-shot learning because few-shot learning involves kind of referencing obviously things in the context. And then in general, it's not like performing too well as a long context model. So what Mamba does is trying to improve this. And so their version is called S6. So selection, I guess. And for some reason they add on like two S's onto the number, um but anyway, so now we have this selective S4 model. And you could see that the key difference here is that now this parameter is actually a kind of output of the model. So you take in the current input and you have, say, a multi-layer perceptron, and it actually outputs a parameter that's then discretized and kind of passed into the state space model. Okay, so now you have something that is time varying. It can kind of change the transformation based on the current input. And so it can, as a result, kind of select from or modulate the information flow a bit. Now, if you think about it, this kind of breaks one of the nice parts of the formulation. So now it turns out to be difficult to parallelize the model because now we have this time dependence and it's kind of easier to, more difficult to just break things apart independently. So what they have to do is use this kind of clever thing called a scan. And you can parallelize this kind of scan operation a bit. So here is the kind of diagram. So the observation is that you can still break some of the computations apart and then kind of merge them and eventually get everything at the end. And so now it's not perfectly kind of linear, but it's you can get some parallelism and some speed up. So you'll also see this come up, and yeah, they use this parallel scan, and then another part of the Mamba paper was going in and implementing some CUDA kernel, which does this kind of efficiently on the GPU memory. Okay, and then finally, what does the name Mamba refer to precisely? So Mamba is actually some specific block that incorporates this S6 kind of operation that we saw before. So when you incorporate the S6 into the overall model, there's still going to be nonlinearities like in the neural network, just not within the SSM block. And so Mamba was this like specific design, and yeah, it looks like this. Okay, so now once you have a block, you can stack them together, and now you have a full neural network architecture. So here's some of their results. So it's a bit small. Let me just talk through them. So the first one is on text data. And here on the y-axis, we have the perplexity. So remember, lower is better. And here they were doing pre-training. So you can see the flops that are spent during pre-training on the x-axis. And then here, at least in their experiment, you could see that the Mamba model is basically matching this transformer. The reason it's called Transformer plus plus, actually, I think I put this in the Transformer lecture. This is the Transformer with some of the upgrades from the original Transformer, which is shown here. So like you might have the grouped query attention or better embeddings, things like that. Um, but here they're able to kind of match the performance in their setup. And then here we're looking at kind of very long sequences. So you have this genomic data, which I mentioned at the beginning of the lecture. You're going up to 10 to the sixth. And again, audio data can be very long. You could have like a whole podcast or something. And so again, going up to 10 to the sixth. Here, I think maybe they couldn't even use the transformer for their experiment, but you could see the comparison between Hyena was the model that had this like hippo matrix. So you could see that whatever they did in Mamba is kind of important. And then here again, yeah, you have this S4 model and the Mamba's improving upon it. Again, here lower is better. Okay, so then since then, this is another one of these papers that, it came out a few years ago and has thousands of citations. So this kind of led to a lot of excitement in the area, and there's been a lot of follow-ups, things like that. And again, this was really kind of pioneered by Albert Gu, who's now here at CMU. So maybe you can go talk to him or something if this is interesting. Okay, so to recap, the state space models, at their core, they're trying to combine these insights from kind of recurrent models and convolutional models. And they're trying to get the best of both worlds, so have both efficient training and efficient inference. And to recap with the long context models, we talked about some concrete examples of like benchmarks and different tasks you can do. Then we talked about improving transformers. So the quadratic constraint we have on memory and trying to improve that. And then also trying to improve the embeddings that are used for extrapolation. And then we just talked about these transformer alternatives. And again, this is just one example, but there's really active research on trying to come up with other alternative architectures. And one of the key motivations is having really fast inference or supporting really long contexts. So really for the more kind of cutting edge methods, we would need another lecture or guest speaker, something like that. But just know that this is another kind of active area of research. Okay, so that's all I have for today. There's time for maybe like one or two questions, or I can take them here in person.